Okay, so this is a review of Chapter 4 for you chemistry students that want to have a little bit of extra practice on what's going on for our test coming up. Some things that you'll want to know. Chapter 4 we were talking, it was our first chapter where we actually started talking about the atom, and there are several things that first of all, one of the things you'll want to know, and there's nothing for me to really draw for you here, but I'm just going to tell you, you'll want to know about Dalton's atomic theory. So you want to be able to list the 5 different components of Dalton's atomic theory. What is it that Dalton believed in with his theory? Of course, now with Dalton's atomic theory, of course, we are talking about the atom. And with the atom, we know we now have, remember at one point, we didn't know that there were subatomic particles, and now we know there are. And we know with the subatomic particles, we have 3 different types that you're going to be responsible for, at least on the test for this class. And one is going to be the proton. You'll have to know that there is an electron, and then you'll also want to know about the neutron. And of course, the proton is positively charged, the electron is negatively charged, and the neutron has no charge at all. What's also important to know is that the proton, not the electron, and the neutron are in the nucleus of the atom. So I guess I can draw this out for you. If I were to have an atom, and let's use the atom lithium. Lithium has an atomic number of 3, and as you know, if it has an atomic number of 3, that means that there are 3 protons in the nucleus of that atom. And then also, if along with protons in the nucleus, we have electrons, so we're going to say that there are 3 neutrons in the nucleus of that atom. And then we have, of course, the electrons, and the electrons are not in the nucleus. The electrons we're going to find, even though this is not really true anymore, we're going to pretend like they're traveling around the nucleus in some kind of a fashion, something like this. Are you done? Okay, you do good on it? Okay. And we may find an atom over here, an electron over here, maybe an electron over here, an electron over here, an electron over here, and we know they're going to be, I want to say flying, but they're going to be in some kind of a pattern about the nucleus, but not in the nucleus. So a part of the nucleus is going to be the protons and neutrons, and then we have the electrons that are not a part of that nucleus, and the electrons are right there, and they are not a part of the nucleus. So we also know that the electrons, when we talk about a couple of things we want to know about atomic number. Atomic number is the number of protons present, the number of protons present, and that never changes. The number of protons will always be the same, and the number of protons is what makes the element the element. Neutrons can change, electrons, as we're going to learn, can change, but protons will never change. So the atomic number is the number of protons, and then we have the mass number, and the mass number is the number of protons plus neutrons. And the mass number, you can also think of the mass number as the atomic mass, or the atomic mass units, and we're going to see about that in a little bit. And the reason why that is because most of the mass of the atom is found in the nucleus, because we know that the protons and the neutrons weigh more, or they mass about 1,840 times more than an electron. I think I'm running on the bottom of the screen here, so I'm not sure you're able to see what I'm doing. So let me see if I know how to use my pen. See if I can bring this up a little bit. Let's see if it scrolls up. We'll find out in a minute when I replay this. And if it does, we'll know that the electrons, matter of fact, I don't think you have to know this for a test, but I'm just going to tell you, a proton has a mass of 1.67 times 10 to the negative 24th. That's how small or how little a proton weighs. And interestingly enough, we know that protons are heavier than electrons. Electrons, and then you'll understand why they're not involved, or they're not calculated in the atomic mass or the mass number. Electrons have a mass of 9.11 times 10. Are you ready for this? To the negative 28. That is incredibly small. About 2,000 times smaller. We had about 2,000 times smaller than the mass of a proton or a neutron. So let me erase this here. I've learned that if I pause and erase, when I come back, I have a black screen for a long time. So bear with me while I just go ahead and erase this out, and you are witness to that. And I don't know what's going to happen when I scroll back up, so it's going to be kind of interesting to find out. I'm also finding out that I only have about 15 minutes to video at one particular time. If I take longer than that, then I lose my information. So get this back where it needs to go, erase that out, and then we'll get back to, we're almost done with chapter 4, by the way. We could talk about Rutherford's gold foil experiment. And there are some things you obviously need to know about that. Let me write that down for you here. With Rutherford, with his experiment, that was called the Rutherford gold foil experiment. And with that, he shot alpha particles. If you remember, he shot alpha particles at a piece of foil. So these alpha particles came streaming out. And they were going through some foil. So he had some gold foil set up. And then beyond the gold foil, he had some kind of device that was able to capture and measure those alpha particles to see where they were going. And what he found out, he thought that the gold foil protons, the nucleus, the protons were distributed throughout the entire piece of foil. And actually what he found out was very interesting. When he shot these alpha particles, which by the way were positively charged particles, as they were coming in through, most of them just passed right on through and made connections with the back. Came right on through, right on through, right on through. And what he noticed is occasionally he would find one that would hit and then deflect off a little bit. And then also he found others that would come in to have greater angles of deflection, and there were occasions where they would come and deflect almost right back. So when he gathered that information, he then realized that in fact atoms are made up of mostly space. You have your protons and your neutrons inside the nucleus. Then you have your electrons distributed throughout, depending on how many electrons are in that particular atom. And you see that this is mostly made up of is space. So that's what he concluded through this gold foil experiment, that they're made up mostly of space. Now that isn't the only thing he concluded, but that was one of the more prominent things that he was able to uncover. So I'll erase that. And the last thing I'm going to end up with on this lesson, because we only have about 2 or 3 minutes left, is we're going to talk about this idea of isotopes and what isotopes really are. And you'll want to read in your book and make sure you're up to speed on the whole isotope thing, because I'm sure it'll be on your test. But when it comes to isotopes, let me just write that down for you. Isotopes are differences of the same element. And what's different about them is the protons are the same. I'm just going to put a P for protons are the same. So for example, if I have carbon, carbon has 6 protons. So we have carbon that has 6 protons, and it may have a mass number of 12, meaning that it has 6 protons and 6 neutrons. Another form of carbon that we see in nature has 6 protons. They always do, but it may have a mass number of 14, meaning it has the difference between 14 and 6, which is 8, means that it has 8 neutrons. So when we're talking about that, then we realize what we're saying is that carbon 12 actually has 6 protons and 6 neutrons. Carbon 14 has 6 protons and 8 neutrons. That's the big difference. And then if you were to have something like, I don't know, let's just say carbon 18, it still has 6 protons. That never changes. So it would be carbon 18 has 6 protons and 12 neutrons. That's what makes an isotope an isotope. It has the same amount of protons, it just has varying amounts of neutrons. And this goes along with this idea of relative abundance. Relative abundance. And relative abundance simply, see you, Jack. Relative abundance simply means the amount, or I guess you'd say the percentage that that atom would be naturally occurring in our environment, in our universe. So think of it this way. Think if you had there's all these, let's say we have all these carbon atoms out there floating in the air, hypothetically. Okay, we're just playing with our imagination here. And I had a giant carbon net, and I can just get my net and just grab up the whole slew of carbons. And I lay those carbons out, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 14 carbons. And as I'm counting the carbons, I see I have different types of carbons. I have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons that have 12 neutrons, maybe 2 carbons that have 14 neutrons, and maybe 1 carbon that has 1 neutron. And based on the mass of that carbon, carbon 12, is going to be, we're just making up numbers here. We're going to call this, it's going to say it has a mass number of 12. Carbon 14 is going to be closer to 14, and we're going to call this carbon 16. I didn't give it a name, I don't think, or maybe I did, I don't remember. Carbon 16 there's only 1 carbon 16. So we see that we have 1, 2, 3, 4, 5, 6. We have 10 carbon 12s, so that's going to give us 120. We have 2 carbon 14, which is going to give us 28, and 1 carbon 16, which is going to give us obviously 16. And I got to scroll. I think I'm losing the screen here. And then I add these up, and I have 120, 140, 150, 158. I have 164 total, mass of 164, and I'm going to divide that by the fact that I have 13 different carbons. So if I do the math here, I see that that's a 1, that's a 13, it's going to be a 3, and a 4. 13, 26 is going to go 2. It's going to give me 26 with a remainder of 8. So I'm going to have 12.8, we're going to say, is going to be the atomic mass, or the average mass of all the different carbons. And we see that 12.8 is closer to 12 than it is to 14, and that makes perfect sense because that tells us we knew that there were more carbons anyway, more carbon 12s, and this confirms it by the fact that the mass is only 12.8. So that's it for Chapter 4. Good luck on your test, and we'll see you in class.